Good evening, students. Okay, in this class, we are going to discuss the rest of the questions from 2014 paper. Excuse me. Sorry, I forgot to put the recording. Okay, very sorry. Okay, it's going to be a. Oh, we can't do anything. Okay, students. So now, when you remove this, the voltage at this point X is increasing by how much? 4 volt. Okay. So it was okay. So when you remove this, it increases by 4. Okay. So now let's just remove and look at the circuit. So now still it is earth. Okay. So here, what is the point voltage? It is 12 volts. Sorry, 0 due to the earth. Okay, the earthing causes 0 volt here. So this is the negative terminal. So I said that when the charges goes from the negative terminal to the positive terminal, the potential of the charges is increased. So it is increased by a value which is equal to the E, electromotive force. So what is the point voltage in the positive terminal? The negative terminal is 0. Positive terminal is 12 volts. So now, according to the voltage divider principle, directly proportional to the resistances, the voltage drop is going to occur. So the voltage difference between the total voltage difference between these two resistors is 12 volt. They are equal in magnitude, the resistance. So this should have a drop of 6 voltage, and this should also have a drop of 6 voltage. Okay. So now, what is the point voltage of this point? Vx after removing the R dash. Huh? What's that? 6 volt. Okay. So difference is 6. And if it is 0, this should be 6. Or here 12, the drop is 6. So this should be 6. So what is the previous volt here? Potential. Previously, when R dash is connected, it should be 2. So now we can say it increases by 4. So now, according to the voltage divider principle, again, this whole system, I mean, these parallelly connected resistors actually have a drop of 2 volt. So this should have a drop of, so 2 is gone, it is 12. So it should have a drop of, volt. Yeah, 10 volts. Yeah. So what is the ratio? 10 volt is to 2 volt.
1:5.
5:1. Yeah. So for this one, it is 5. For this part of the circuit, it is 1. So we already said that the voltage drop is directly proportional to resistance. So can you actually predict? Can you actually work out the resistance of this part, the equivalent of these two resistors? Yeah. Voltage is 5:1. So resistance should also be 5:1. So if it is R, this should be R by 5. The equivalent should be R by 5. We know the equivalence. I mean, we know the formula to find the equivalent resistance of two parallelly connected resistors. 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So here R equivalent is R over 5. So this should be the reciprocal. So 5 over R, and this should be 1 over R dash, and this should be 1 over R. So we should find the R dash. So when you take this to this side, subtracted, so R by 4 is the answer. R dash is equal to R by 4. Okay, so what's the correct answer? It is the fourth answer. Okay, are you all clear? We are using this principle, voltage divider principle. Okay, so for this part, these two resistances are connected serially. So we can apply the voltage divider principle. So what's the next question? This is a very traditional kind of a question. These kinds of questions are repeatedly count. They repeatedly count. So you should do some focus practice here. You should compile all these types of questions and practice. Then only you will become familiar with solving these types of problems. So now, so this is what? The center. Okay. So there is a beautiful diagram there. Yeah. So we shall try to draw this carefully. I mean, you know, so it comes like this. Okay, the current flows like this. Do you know Biot-Savart law? Huh? What does that say? When there is a current carrying conductor, okay, when there is a current carrying element, so if it is like this, for example, so you take a small element of length delta L and you take a small element of current I. Okay, so this delta is usually small delta. So what is the equation for the magnetic flux density at this point, which is distance r away from that element? Huh? According to Biot-Savart law, B is equal to, tell me. This angle is theta. Okay, now tell me. Mu naught over 4 pi, then
ideal sin theta.
yeah, I delta L sin theta over what else? One is missing. R square. R square. No? So what is mu naught here? It's magnetic permeability. Okay, in the free space. So this is the equation. According to this equation, I mean from this equation, we can derive any equation for magnetic flux. Many equations for magnetic flux densities due to several structures. So one of them is the ring. Okay, a loop, a circular loop, a ring-shaped loop conducting electricity current like this. So we can actually find the magnetic flux density in the center of that loop. So what is the equation? If the current is I, if the radius of that loop is R, yeah, what's the equation? B is equal to mu naught I divided by 2R. Okay, so this is for a complete circular loop. Okay, here you have some circular structures. We shall analyze that later. So what is the equation for the flux due to a very long current carrying conductor at a distance of R from the conductor? What's the equation? Huh?
Mu naught I over 2 pi R.
I over 2 pi R. Very good. So what else you have? Solenoid along the axis of the solenoid for a very long solenoid. What's the equation? You know? N I. What is N here? N is number of turns per unit length. So now you have different parts of conductors here. So one is coming like this, then it turns like this, and this comes like this, and after like that, and like this, and then it leaves. Okay, so now can you just tell me whether this particular part of the conductor, this particular part of this diagram, could cause a magnetic flux density here? Can that cause? Will that cause? So it's a linear conductor. Will that cause? It cannot cause. So see, a linear or very long conductor carrying like this can cause a magnetic flux density, magnetic flux here, okay, from a distance r. But this is coming towards this point. So if you measure the distance from the current, there is no distance because it's coming towards this point. So all these components, the linear components of this circuit, are actually useless, only to carry the current. They don't have any there is no magnetic flux due to those parts in the center. But these circular parts will have, okay, will have. So it is R, this is small r, this is also R. So the radius of these parts are actually 2r. So how are you going to write the equation for the net magnetic flux density? So a piece of wire is bent into the form shown in the figure and the current I is passed in the direction shown. The magnitude of the magnetic flux density at the point O is. So how do you find that? So due to this circular loop, there will be a magnetic flux density, and due to this, there will be a B. Okay. So let's find the direction. So what law do you use to find the direction of the magnetic flux density? Maxwell's
Right hand thumb law.
Yeah, right hand law. Yeah, right hand law. Yeah. So you have to keep this finger, you have to keep the hand like this first, and then this shows the direction of the current, and this shows the direction of the magnetic flux density. So due to this, it will be outside. No? So I will just label here. Due to this, outside. Okay. Due to this, going inside. So when you find the net magnetic flux density, so you have to actually subtract. I mean, you have to find the algebraic sum of these three components. So what do you think? So this is 90 degrees, okay? So this is quarter of a circle, and this is also quarter of a circle. This is 3/4, okay? So let's write for this one, this part, because we know that this will be the predominant one because it has a lesser radius and also it has a 3/4 of a circle, no? So how do you write? First, put the fraction. So it's 3/4, so 4, the 3 divided by 4. Then into, now write the equation, this, mu naught I over 2r. So mu naught, substitute the I, yes it is I, 2r, yeah the r is r, so 2r, just like that. So now you have to subtract, okay? You have to subtract the magnetic flux density due to this. So can you consider these two as a half circle? Can you? This is a quarter, this is a quarter, both form half. Okay, half of a circular loop. So put the fraction as half and then write the equation. Mu naught I over 2. You leave mistake here usually. Put 2 into the r. So r is 2r here. So don't forget that. There are two 2's. Okay, one 2 is that's in the equation, the other 2 is for the r. Okay, according to the data, you have to substitute. So now you know this is 8, this is 8. So when you like subtract, the LCM is easy here. So 8r. So 3 mu I minus 1 mu I is 2 mu I, mu naught I, sorry. So this is 4. Now mu naught I over 4r in which direction? Direction? which is
Inwards, sir.
yeah, inwards. Good. Then 28th question. So I'm going to introduce you like a shortcut for the 28th question. First, we shall analyze the theory. Okay, now, so this is about the waves, the standing waves created in a stretched string. Okay, now two identical strings are placed separately subjected to a tension P. When plucked at the middle, each string produces waves of frequency F. Now, if the tension of only one string is reduced to 0.81 T, the strings are plucked at the middle simultaneously. 5 beats can be heard during 1 second. The value of F is. So why do you hear beats? Yeah. Yeah, you know the superposition of waves. Superposition of waves cause 3 effects. What are the 3 effects of superposition of waves? One is interference, then beats, then I'm telling you everything. What's the only one left? Huh? I said yesterday also. What is that one thing I didn't tell? Tell. Huh? What's that one thing? It's standing waves, okay? So now there are 2. So we don't know the overtone here, but they are like initially they are resonating. Okay, both have the frequency of F, so it's like resonating. So both should have same overtone, isn't it? So there is no chance for these 2 identical strings to resonate with different overtones, no? Yeah. So the same overtone. Okay. So whatever the equation, you have some constant components. V is equal to F lambda is applicable here. Okay. So here I'm not going to substitute anything for lambda because it changes according to the overtone. But I can substitute T over M for B. Okay. So F into lambda. So F is equal to 1 over lambda square root T over M. So if it is a fundamental overtone, the lambda is 2L. Okay. So I just don't want to substitute it because we don't know about the overtone. Okay. So, but we know this thing. We come to we can come to some conclusions. Okay. So when others are constant, we can relate the F with the some parameters. For example, if M and lambda are constant, F is directly proportional to square root T. If others are constant, F is also indirectly proportional to square root T. And what about square root M? Sorry. And F is also directly proportional to 1 over L without square root. Okay. When other 2 are constant. So like this, you can write. So now, what is the factor that is changed here? It is the T. So this is the relationship that we are going to use. Okay. So one is T. The other one was also T, but now it is 0.81 T. But it remains the same. Now they are hearing a beat of 5 hertz. Sorry, 5 hertz. So let's say that the unchanged ones still have the frequency of F. So what should the frequency of this string be?
F minus.
Yeah, we know that it is going to decrease. So it is reduced. So frequency is also reduced. So it should be F minus 5. So what I do is I just put F over F minus 5 is equal to within root T over 0.81 T. Okay. Don't worry about these relationships. You know that there should be a fraction here. And if one is F, but another one should be F minus 5. Okay. And you have to write an equal ratio here. And here there's a smaller number. So you put a smaller number here and a bigger number here. So that's how you write. Okay, don't think much. So if you know the theory, you can just write this straight away. You don't have to think about these things. Okay, now just simplify it. So T and T are cancelled. So now you know it is very easy to, yeah, it is 0, it is actually root of 0.81 is 9. Okay, so now if you simplify, f is equal to what? 50 hertz, am I correct? 50 hertz. Okay, still like they are having same overtop. Okay, so the lambda remains constant, m is like unchanged. Okay, they are not telling anything about m. Usually we don't change m. So identical strings, so they should have same linear density. So only the factor that is changed is t. So we have to apply this relationship. So I'm writing ratio straight away. Okay. So where should you start from in the exam? From here. Okay. You have to train yourself. Okay, to achieve that kind of a speed. Okay. You should be faster than others to complete the paper within 2 hours. Huh? Any doubts?
Excuse me, sir.
Yeah.
Is this class for A-level?
Yeah. Fine. Yeah.
Yes,
No
I'm
level
asking
student.
all-level. Yes, sir.
This is A-level class. Physics. I mean, I put physics. I don't put A-level physics. Okay. Usually, O-level students they say the science. No, there are separate classes like physics, chemistry. Usually they don't know. So that's I think in the future I have to put A-level, no, in the poster. So many O-level students asked me about the seminar through WhatsApp. I said that it was for A-level. Okay, then.
Don't you keep for O-levels?
No, sorry, I don't usually teach.
It's okay, sir.
Okay, then 29th question. An electron and a proton travel with equal speeds around two circular paths shown in the diagram. Drawn not to scale, okay? Not to scale. The paper will not be enough if you draw according to a scale. So now under the influence of a uniform magnetic field, if the direction, under the influence of uniform magnetic field, if the direction of magnetic field is perpendicular to the plane of the paper. So now they are telling statements about the direction of the circular motion and also to identify which motion belongs to which particle. Okay, so now let's analyze the circular motion of charges when they are sent perpendicular to a magnetic field. So imagine that there is a uniform magnetic field like this, and you are sending a charge of plus Q. Okay, now it goes. Yeah, it goes into the magnetic field, and now you are filling all the area with the magnetic field. Otherwise, it will come. Okay, it will come back. Okay, so now you have, after sending this, you have filled the rest of the areas, the surroundings also with the magnetic field. So how do you find the direction of this? How do you find the direction of deviation of this particle? So
Fleming's left-hand rule.
Yeah, Fleming's left-hand rule. So now it is inwards, yeah, and the current, it's a positive charge now, so in the direction of the velocity. So now the force is like this. So the force is perpendicular to the velocity. So that thing is very important. So as it is perpendicular to the velocity, always perpendicular to the velocity. After a small deviation, again it becomes perpendicular. After small deviation, again becomes perpendicular. So it remains perpendicular. So the change of the velocity will also be perpendicular to the tangential velocity. Okay. So change of velocity is perpendicular. So there should be an acceleration. Okay, perpendicular to the velocity. So there should be a force. So that kind of a thing will lead to a circular motion. So if there is a constant velocity change in the direction of the center towards the center, okay, so that produces circular motion. So now it's going to move it in a circular path. Okay, so now I will draw it here. Okay, in the middle. So like this. So it will move in which direction? Clockwise or counterclockwise? So this is counterclockwise. Okay. So if it is a negative charge, so if it is minus Q, Yeah, if it is moving in this direction, so the magnetic flux is like this. And what about the current? It's a negative charge. So the current is opposite to the direction of the velocity. So its deviation is going to be like this. So it will also produce a circular motion, but in clockwise direction. Okay. So what are the equations that you can take for these kinds of motions? Yeah, you have to write the equation for the circular motion. For what? For the centripetal force. So what is centripetal force? That's the equation for centripetal force. M V squared over R. Am I correct? So it is equal to BVQ. This is the force acting on a moving charge in a magnetic field. So now you can cancel V's. So you get the equation MV over R is equal to BQ. So now you can take you can derive an equation for R. So this is MV over BQ. So now you can find the determinants of R here. So R is directly proportional to M, directly proportional to V, directly proportional to B, directly proportional to 1 over B, 1 over Q. Okay. So these are very important. So now they are explaining about the initial velocities of these two. I mean, the electron and proton equal speeds. Okay. So now this factor, the B is same magnetic field. V is also same. So what is the factor that is going to determine R? M over Q. So this is greater for electron or proton. The magnitude of Q is same. So electron, which has a higher mass?
Proton.
Proton. Yeah. So the bigger circle should be for the proton. So yeah, electron, as it is a negative charge, it travels in the clockwise direction, and then it has a smaller path. Okay. So small circular path. So the first answer is correct. Okay. Now shall I ask you a question? So you can also derive the equation for V here. So V is equal to what? V is equal to BQR over M. So can I say that V will increase when you increase B? Can I say with increasing B, V will increase? Is it correct to say like that? Will it change the velocity? It will not. Okay, why is that? Because the force is always perpendicular to the motion. So the velocity cannot change. It is not tangential force. It's not a tangential force. It is a perpendicular force. You cannot have an acceleration in a horizontal motion due to weight, no? Okay, weight is a perpendicular force, perpendicular to the horizontal motion. So you cannot have an acceleration due to weight. Like that, you cannot have an acceleration in the tangential direction. I mean, you can have an increase in B due to B. Okay, when you increase B remains constant, but what changes is R. R reduces. Oh, here. So when B increases, R reduces. So the only factor that is manipulatable is the R. Other B is not changed. So if you change others, you will see a change in R. So R is the only factor that changes. Okay, remember that. They may confuse you. If I give this equation in the paper, okay, I'm giving a question like this. So after explaining the scenario, the V is related to these factors like this. I'm giving the equation, the question itself, and I'm making statements using that equation. So, you are more likely to get the wrong answer because they are like deviating you towards the wrong answer. Okay, so be careful about that. V never changes. So, 38th question. Identical loops in 3 arrangements, A, B, and C of circular loops entered around the vertical axis carry equal currents in the directions shown in the figure. In the arrangement C are 2 separate loops very close to each other with a common center at X. In all 3 arrangements, the loops are separated by a distance xy, and P is the midpoint of xy. The magnitudes of the magnetic flux densities at P in the arrangements A, B, and C are BA, BB, and BC respectively, then the relationship is asked. So how do you find? Yeah. So this arrangement is very unfamiliar for us because you know, like, sorry, this line is unnecessary. Sorry. So if you have a loop like this, okay, circular loop, okay, so it carries current like this, yeah. So now you have a magnetic flux, a magnetic field due to this current. So how do you find the direction? Yeah, using this right hand rule, yeah. So now like this, there will be a field line. Okay, this is not a force line, it's a field line through the center. And the others will be like this. Okay. Okay, so now you have equation for the magnetic flux density in the center. What's that equation? V is equal to mu naught I over 2R. But here the scenario is different. They are giving loops, but they are asking about the magnetic flux density is at a different point. We don't actually have an equation for that. Do you have an equation? To write here. Do you have an equation? If you have, just tell me. We don't have, no? Usually we don't have an equation for the magnetic flux density here at this point. But we know that there will be a magnetic flux density. Yeah. So this is like a point here. Okay. So a line is going now. So that's going to have some amount of magnetic flux density. Okay. The density will also reduce with the distance. Okay. So see here they are dense, but when you here, when you draw a unit area here, it catches only one line. But here, if you draw the same area, it catches 3 lines, for example. So the density is higher here and it's reduced with the increasing distance from the loop. But it has some B. Okay, it has some B, but we can't write any equation. Okay, it has some B. So now let's consider the diagrams. Let's analyze the diagrams here. So now the first diagram is like this. So now can you determine the directions of B magnetic field density? So now the direction is like this due to this loop, and direction is like this due to this loop. So both of them will create magnetic flux density in the same direction here. So you should add these two magnetic field densities by these two loops. And here, can you find? So this is in the direction of this, and this is in the direction of this. Okay. So now it creates a magnetic field in this direction, and this creates a magnetic field in this direction. So they are going to oppose, or will they oppose? Yeah.
0.
Yeah, it will cause a 0. 0 magnetic flux density in the center. Why? Because it's the midpoint now. So we know that the magnetic flux density decreases with the distance. So as these two are conducting same amount of current, the variation of the magnetic flux density with the distance will also be the same. So both will create B of same magnitude but in opposite directions. So there should be a 0 flux density. And this diagram, there are two carrying the opposite directions. So what do you think? They will cancel significantly, no? One is a little bit above, but they will cancel significantly. No? Opposite and So the opposite, they will cancel each other. So now the resultant will be due to the one here. Okay. So here the magnetic flux density is due to only this one because they will almost cancel completely. Here it is absolutely 0. Here you have to add these two. So this should be the highest, BA. This should be the lowest, and this should have an intermediate value, BC, and the last one is BB. That's 0. So what is the order? So BA, BC, and BB, second answer. 31st question. I have already explained this. Okay, so I will explain it again. Okay, 3 different types of thermometers, P, Q, and R, having a temperature range of 0 to 110, and keep at room temperature of 30 degrees Celsius were simultaneously dipped into a large oil bath, maintained at 100 degrees Celsius at the time T is equal to 0, and their readings theta were recorded with time. Curves in the figure show the variation of theta with T for these three thermometers. Consider the following conclusions made about the thermometers after analyzing the 3 curves. So now we are going to analyze the 3 curves. So the curves are like this. So this is the graph of theta against the time. Okay, so this is the 100 degrees Celsius level in the graph. So there are 3 different graphs. One is for P, a linear graph, Q, linear in the initial part, but curved in the later part. This R, the Q is there. Q is showing a reduced, final, stable reading. Okay, so now, the first question is, which thermometers are showing the correct reading? Yeah, except Q. Other 2 are showing 100 degrees Celsius. So Q is incorrect. Okay. So what property of thermometer is lacking here? It's what property of the thermometer is lacking? Accuracy. Okay, accuracy is low for Q. Okay. So other 2 are like, other 2 are correct readings. But you can say one thing about the R and P. The P is faster than R. Actually, Q is also faster than R, but Q is wrong. Okay, so those are the things that we can actually we can find from this particular graph. Okay, let's analyze the statements. The first statement is P is the most sensitive thermometer. So what is sensitivity? Sensitivity is about how much, to what extent the thermometric property changes with the temperature. So if I write an equation for sensitivity, that will be like this: delta X over delta theta. So this is the change in the thermometric property. This is a change in temperature. For example, if I take the temperature changes 1 degree Celsius, one thermometer is showing the thermometric property difference like 50 units, whatever the unit. Okay, it can be pressure, it can be, according to the thermometer. And the other thermometer is showing a change of 20 units. So now, which is better? This one is better, okay, in terms of sensitivity. So what is the advantage of having a higher sensitivity? You can actually detect even small changes, minute changes in the temperature. So among the thermometers in your syllabus, what thermometer has the highest sensitivity? So what are the thermometers in your syllabus? Yeah, it's liquid thermometer, liquid in glass, mainly mercury. What else? Thermocouple. Then thermistor was there, but these days they say that it has been removed from the syllabus. But thermocouple has higher sensitivity when compared to the liquid thermometers. But another thermometer which is not in your syllabus has a higher sensitivity. What's that? constant volume gas thermometer. Okay, constant volume gas thermometer. So gases expand, yeah, they expand massively. Here it's constant volume, but the pressure changes. Pressure changes are very high, very detectable, and the sensitivity is very high. So that's how we talk about sensitivity. So when it comes to a mercury thermometer, so how does the sensitivity changes? Yeah. So you have some amount of mercury here. So due to the expansion, the increase in volume is pushed into this capillary tube. So that expansion delta V, expansion in volume, is given as V naught into gamma delta theta. So this is temperature change. So what property that determines the sensitivity here? It is the change in the length, no? The length of the mercury column. So now I'm going to divide this delta V by A, the cross-sectional area of the capillary tube. So both sides. So now it gives you delta L, the change in the length. Sorry, length. So now this can be substituted with, so it's the same equation substituted with pi r squared, because the capillary tube has a circular cross section. So now to increase the change in the length of the thermometer, you should reduce the radius. You may increase the volume. You may select a liquid with higher expansivity, okay, for unit temperature. Okay, so expansivity is same usually because we use the same kind of thermometers, thermometric liquids. So, so V naught and R are the factors that are going to determine the sensitivity. Can you tell anything about sensitivity using these graphs? Huh? Can you come to any conclusion regarding sensitivity?
No.
No, because you don't have any detail about the change in the length. It is the graph for theta with time. So you can't tell anything about the sensitivity. The next is the thermometers P and R are accurate but not Q. So that is very obvious. Q is not accurate. Then the scale of the thermometer R is not linear. So the scale, how do you make a scale for thermometer? How do you calibrate it? So usually what you do is you draw a graph with theta for, graph for length with theta. So actually that is your, this graph for this equation, okay? So for example, one thermometer is like this, another thermometer is like this. What does these two graphs imply? So if it is A, if it is B, so we can tell one thing, that per unit temperature change, the change of length is higher in A, so A has a higher sensitivity. Okay, so now when you calibrate the thermometers, which thermometer will have increased gaps between the adjacent temperatures? Huh? Which thermometer has increased distance between the adjacent temperatures? A, because the length is higher per unit temperature change. No, so like that, another thermometer has a change like this. So now, so for example, here it is 5 degrees Celsius. Here it's 10. Here it's like 20 maybe. So for 5, it has a thermometric a length. Okay, it has a length, and this also has a length, and this also has a length. But you don't see a linearity, isn't it? So usually this length should be twice the length. I mean, for 10 degrees Celsius, the length should be twice the length for 5 degrees Celsius. For 20, it should be twice the length for 10 degrees Celsius. But it's not like that, because it's like decelerating. Not deceleration, I'm just telling the gradient is reducing, decreasing. So this particular liquid, this particular thermometer, for example, C, cannot have a uniformly calibrated scale. No, the gaps will be changing. So these thermometers need a graphical. You first should graphically you should graphically find the variation of length, and then you have to calibrate. You can't just find 2 points and divide the rest of the length as equal scales. You cannot do that. You have to use the graphical method. Okay. So the graph should be for length with temperature to determine whether it has a linear scale or a non-linear scale. Not this graph. This is with time. Now you can come to only one conclusion. This has a non-linear expansion with time. It's only the time that is affected. It is only the linearity with time. Okay, not with the temperature. Okay, so you can't come to a conclusion like we are mentioning in C. The next question is a very interesting question. Breakdown voltage of the Zener diode in a circuit shown is 5 volt and RL is a suitable resistor. The capacitor C is first charged to 10 volts by closing the switch S1. So you now charge the capacitor and opening the switch S2. Subsequently, S1 is open and S2 is closed. Consider the following statements made about the functioning circuit after S2 is closed. Okay. So what is a capacitor? Why do you use a capacitor? What is the purpose of a capacitor? Just tell. Why do you use a capacitor? What is the function?
Store charges.
Yeah, to store charges and to supply whenever the charges are necessary. So first is store charges. First it should accumulate the charges. So that process is called what? Charging. So when it supplies charge, that process is called discharging. Okay, so the capacitor is first charged here, then discharged. So that is the question. So this is Zener diode. So Zener diode is a special diode that is made, that is actually manufactured to function in the reverse bias state. Okay, so it has something called Zener voltage. Okay, Zener breakdown voltage. So at one stage, when the voltage difference across a Zener diode exceeds its breakdown voltage, that Zener diode breaks. After that, it maintains a constant voltage difference across its terminals. Okay, and also whatever that is connected parallel to that Zener diode. Okay. So this is R, this is R dash, and this is Zener diode. So it doesn't have a name, but the VZ is equal to what? The breakdown voltage, 5 volt. So now the capacitor is charged. The capacitor is charged until until the voltage difference between these two plates become 10 voltage. Okay, it's charged completely. So now you have open, and now you are going to close this. So after charging, you close this. So what will happen? This will supply the charges to this circuit. Okay. So do you know the variation of voltage and also the current and also the Q, the charge stored, when a capacitor is being discharged with time? Okay, with time, the variation of V, Q, and I flowing in the circuit. Do you know? So when it's discharged, it rapidly supplies the charge to the rest of the circuit. So the voltage difference between the plates reduces and becomes zero finally. I is also reducing and becomes zero. Q is also reducing and becomes zero. The gradient should continuously decrease. Okay. So now let's only take this graph. Others are not much relevant for us. So initially, the voltage difference between these 2 points is what? 10 volts, because it was initially charged at 10 volts. So now the 10 volt will be supplied to this circuit when the switch is on. Okay, when the switch is turned on, so this will get some amount of voltage and this part of the circuit will get some amount of voltage. So like that. So when there is a Zener diode, you should always see whether it will break or not. So what? How do you see that? How do you check? First, you should imagine a circuit without the Zener diode. Then just distribute the voltage according to the resistances. So these are now connected serially now. So now you are going to divide according to the voltage divider principle. But you don't know the exact values of these two resistances. But one data is there. What's the data? Yeah, the RL, this is RL, not R dash, sorry. RL is actually a suitable resistor. So that is the only data. It's very funny also, no? They are telling suitable resistor. So they want us to think this way, that this resistance can actually take some amount of voltage from the total voltage supplied to the circuit such that it breaks. Okay, did you understand that? It is a suitable resistor so that it gets sufficient voltage difference across it so that this Zener diode also breaks. Okay, so we shall take it like that. So when you actually distribute the charges, this is more than 5 voltage. Okay, for example, 7 is to this is 10, no, 3, for example. Okay, 7 is to 3. So now, will this break? For example, if you take 7 is to 3, will it break?
No.
This is 5, no. Breakdown voltage 5. If it gets 7, will it break?
Yes.
Yeah, it will break. Okay. So now it will maintain the voltage difference at 5 because it has exceeded the breakdown voltage. So it will break. Okay. So it will break. So it will maintain as 5, 5. Okay. 5, 5. Sorry, 5, 5. Yes, 5, 5. So this is falling now. The voltage is falling. Okay, it is coming towards the T. Sorry, coming towards 0. Coming towards 0. So throughout the time where the voltage difference across RL is sufficiently higher than the 5 volts, the Zener remains broken. Am I correct? When the voltage difference across this RL is sufficiently higher than the 5 volts, this remains broken. Okay. So that is the time period you find a constant voltage difference across this part of the circuit. Okay. After that, what will happen? If it is less than the Zener voltage, what will happen? The Zener will not function. It will act as an infinity resistance. So the circuit is now open. It's like open here. So the only resistances, the resistances will, those two resistances will take their part. They will get according to their resistances. They will get their voltages. Now it is not functioning. So you should understand this circuit like that. Okay. So now let's analyze the statements. So first, voltage across RL will be 5 volt as long as the capacitor voltage is adequately above 5 volts. Adequately above. What do you think? So for example, if it is 5, when you distribute the voltage between these two, this is definitely not 5, less than 5. But they are telling that adequately higher than 5. So there is a chance that the voltage difference across this to be higher than 5 volt, no? Because they use that word adequately. So when we think positively, that statement is correct. Okay, I mean positive means, I mean we are using that word to understand this statement like this. If it is adequately higher than 5 volt, there is a chance for the voltage difference across this part of the circuit to be higher than 5 volts. So there is a chance now. So we take it as correct. Then the B, the time period through which the voltage across RL remains constant does not depend on the value of the capacitance. So let's think about it. But how the capacitance matter? Huh? Does that matter first? So yeah, will that affect? Yeah, definitely. So this is discharging of the capacitor. So the discharging process is actually supplying the charge that is stored. So the charge stored is given by the formula Q is equal to CV. So for this 10 volt, to store a higher amount of charge, the C should be higher. So for the Q to be higher, the C should be higher. So if the C is higher, it will store a higher charge, okay, than the capacitance now. Okay, if you increase the C, the Q will also increase. So now it has more charge to supply for a long time. So what will happen to this graph? The discharging, the voltage variation with the time, it will take more time. So the graph will be like this. Okay. Do you see the impact of charge? It will take more time to become, for the voltage to become 0. Okay. It is same for the current and also for the charge. I drew other 2 graphs initially. Can you remember? So all the processes, the discharging process will take more time. Okay. So let's say like this. So this is broken provided that this part of the circuit has a voltage difference higher than 5 volt. So that is possible up to one point. Let's take that point as this point. Okay, for example, at this point, it is at a broken stage, and after that, it is non-functioning. So that is the what do you say? That is the last time the Zener diode was in the broken state. After that, it is not broken because it is less than the 5 volts. So after that, the breaking is not possible. But now, when you increase the capacitance, this charge stored is higher. So the time taken for the discharging process is higher. So the same voltage remains for a long time. For a long time when you increase the capacitance. So in the first instance, it was broken up to, through this time interval. Now, through this time interval. So, does it have an impact? Capacitance. It has. When you increase the capacitance, the charge stored is increased. The time taken for the discharging process is increased. The time through which the Zener diode remains broken increases. Okay. Then what they are telling in the B statement is also increases. The time period through which the voltage across RL remains constant. So that is the voltage remain constant means the Zener diode remains broken. Okay, the same statement. So C, potential drop across R gradually decreases with time. So what do you think? It's R. So the potential difference across the whole circuit is reducing. But the problem is, for some time, this voltage remains constant. But after that, this is also decreasing. Okay. But what do you think about this one? That was always decreasing, no? Initially, even if it is constant, the voltage drop across this resistance should fall. Why? The total voltage falls now. You understand that? So up to this point, you don't see a voltage drop across this part of the circuit. So this part of the circuit, if you draw the voltage difference, for some time it remains as 5 and then it falls. But when you draw the graph for this resistor, so it was always experiencing a voltage drop. Okay, when the Zener was broken, the graph is like this for this, because the total fall is actually experienced here. The reduction in the total voltage is only experienced here because it is constant. But after that, these two resistors share. So there's a possibility that its gradient reduces. No? Like this, like this. So it will finally become 0 at one point. Am I correct? Okay, did you understand? Any doubt? Huh? It's a very interesting question, okay? So what do you think about the graph for I with time when charging the capacitor, and also V T and also Q T when charging capacitor? We try these graphs, okay? So 33, A and B shown below represent logical inputs applied to circuits 1 to 5 given below. And F represents the expected output from the circuit. So now, when you see this, yeah, straight away you can come to an answer. How? It doesn't deserve to be the 33rd question. Okay, so what's the answer? AND gate. So you see, only when A and B are 1, the output is 1. At other instances, the output is 0. So this should be an AND gate. Okay, 34th question. Which of the following is not true regarding an NPN transistor and N-channel field effect transistor? So there are two types of transistors. What are those two types? Don't say NPN and PNP. What are the two types? You all are there? Okay, there are 15 students, okay? What are the two types of transistor when classifying broadly?
BJT and JFET.
Yeah, somewhat
Unipolar,
correct.
Bipolar.
Yeah, unipolar, bipolar is a good classification. Yeah, unipolar and bipolar. So now, what is unipolar? Unipolar is when unipolar only one type of charge carrier is responsible for the current. In bipolar, both types of charge carriers, the holes and electrons, participate in carrying the current. So among these two types, we only study JFET for unipolar transistors and BJT, specifically NP and BJT for bipolar transistor. To be more specific, we study actually N-type JFET here. Okay, N-type JFET. So for a JFET, you draw a diagram like this. So this is the symbol. So there should be an arrow like this. So this is N-type JFET. So what is this terminal, and what is this terminal? This is drain. This is source. This is what? Gate. For NP and BJT. So this is the circuit diagram. It also has 3 terminals. This one is collector, this one is emitter, this one is the base. Okay, let's read the statements. I can explain the theory, but it will take time. Okay. So first NPN transistor, it has two PN junctions. Yeah, it has two PN junctions. One is collector base junction, the other one is base emitter junction. Second, for JFET, they are telling it has only one PN junction. Yeah, when you consider the structure of JFET, it will be like this. So there is, first you have a channel. So channel, if it is N-type, you have to use N-type semiconductor. And after that, what you do is, you insert P-type, or you create P-type around this N-type. So it's like a ring, okay? Ring. So this, when you take this section, okay? What section is that? Longitudinal section. So when you take this section, you see two P areas, but it's actually one, okay? So these two are connected always to show that these are not separate, two separate P terminals, okay? Those are actually part of one P-type part, okay? So it's like a ring which surrounds the N part of the JFET. So this is P part, this N part. So this is drain, this is source, this is gate, okay? So only one PN junction is there. So base emitter junction is forward biased when operating in active mode. So it has three modes: active, saturated, what's the other one?
Cutoff.
Cutoff. So can you actually tell? Okay, can you tell the biasing of the junctions in the active state? So this is forward biased, this is reverse biased. In saturated, both are forward biased. In cutoff, both are reverse biased. Okay. So what is for JFET? JFET, gate source junction is reverse biased during the operation. So here, the gate source junction always has something called VGS. Okay. So it is reverse biased. So why do we reverse bias? So here there is a small depletion layer here. So when you reverse bias, the thickness of the depletion layer becomes larger. So it will constrict the channel. So if you increase the thickness of the depletion layer, the channel becomes narrower. So due to the reduced area of cross-section to carry the current, the resistance of the channel is decreased. So that's how you control the current. Okay. So you actually control the whole circuit using this voltage. So that's why it's called a voltage controlled instrument. But this is it voltage controlled? Controlled by what? Current. It is controlled by IB current. But this is controlled by VGS voltage. So when you give an input, so if you give an input after biasing it correctly, when you are using it as an amplifier, if you give an input like this, a signal, it will change the reverse biasing potential difference. So due to that, the current is changed. So the output circuit, there is a change in the current in the output circuit, and there is a change in the output voltage. So that's how you obtain an amplification in this JFET. So during the operation, this is reverse biased. Okay. Then an arrow is marked on the emitter of the transistor symbol. So that is correct, emitter. And the arrow is marks the source of the transistor symbol. But here it's wrong, it's gate. Okay. So both free electrons and holes participate in the operation of a transistor. Yeah, both types of charge carriers. But here only electrons participate. Yeah, it's N type, so only electrons. In P type, only holes. And the fifth answer, fifth statement, magnitude of the current through the collector depends on the base emitter voltage. Magnitude of the current through the collector depends on base emitter voltage. Yeah, it's correct. Base emitter voltage. So it determines whether that transistor is functioning in active state or saturated or cutoff, so that it actually affects the current. Okay. So if it is reverse biased, whatever the input, the collector current is what? 0. In JFET, the magnitude of the current flowing through the channel depends on the gate source voltage. Yeah, that is correct. Okay, gate source voltage affects the functioning. 35th question. The figure shows a section of a horizontal rectangular tube of height 0.016 meters having a large surface area and filled with a lubricating oil of viscosity 0.072 Pascal seconds. What is the force F required to drag a very thin plate of area 0.4 meters squared with a velocity of 0.02 meter second minus 1 along the middle plane between the top and bottom surfaces as shown in the figure? So it is dragged through the middle plane, okay, with a constant velocity. So what does that imply? Constant velocity means there is no external resultant force. So the force applied should be equal to the drag forces, okay, or the viscous forces given by the liquid. Okay, so now you are going to solve this problem. It needs some amount of thinking, okay? So if you pull this like this, it is moving in relation to the liquid layers which are in contact with this metal. Metal or what's that? Yeah, it is some thin plate, yeah. So this layer will give a force like this. This layer will also give a resistance force like this. So this is similar to the friction that you see in the solids, but it has a different kind of an equation. So what's that equation? For the viscous force is equal to, it is directly proportional to the surface area. So it's directly proportional to what? What is this? Delta V over D. Quickly tell. Velocity gradient. So if you convert this relationship into an equation, you put a constant called viscosity or coefficient of viscosity. Okay, this is the equation. So this is called Newton's equation. Okay, so you can actually derive an equation for eta here. So eta is equal to what? If you send A to this side, the F divided by A. What is this? What is this? What is this? Just tell, what's that? That is shear stress, isn't it? Shear stress. What is this? Yeah, velocity gradient, I already told. So for Newtonian liquids, this eta remains a constant, so that the ratio of these two components is a constant. So when you give F, yeah, according to this equation, there is a viscous force like this and this. So there are two viscous forces, no? One is small f, other one is also small f, because it is traveling in the median plane. Okay, so now the distances below and above the plate are equal. So that is 0.016. The total is 0.016. So one is 0.008 meters. So these two walls are stationary. Okay, so the velocity of this layer is what? V is equal to 0. Okay, this layer is equal to 0. So this layer has a velocity of the plate. So that is what? 0.02 meters second minus 1. What is the surface area? 0.4 meters square. What is the viscosity? 0.072 Pascal second. So now you have to find one F, then multiply it by 2. So F is equal to eta 0.072. Area 0.4. Velocity gradient 0.02 divided by 0.008. So if you simplify this, what's the answer? Huh? Can you tell me the answer? Yeah, yes. 0.072, no? Newton. So this is 0.114 Newton. So it's 1.44 into 10 to the power of 1 newtons. Okay. 36th question. 3 spherical liquid films of surface tension T1, T2, and T3 respectively are in equilibrium as shown in the figure such that the corresponding radii R1 is equal to small r, R2 is equal to 2r, R3 is equal to 3r. Then, so this is very easy. This one also doesn't deserve to be 36th question. Huh? It's very easy, no? So, you know, they are spherical liquid films like bubbles. So this has a radius of 2r, this has a radius of 3r, this has a radius of r, and all are in a closed system. They are kept like this. You know, it is closed. So there is no connection between the atmosphere and the gas inside this system. So you actually have an increased pressure inside these bubbles. Why is that? Because they are bulging into the atmosphere. So they should have a higher pressure when compared to the atmospheric pressure. And also this system is continuous. You see? So there should be a constant pressure throughout all these areas. Am I correct? So the pressure difference between all these films, all these surfaces should be equal. The pressure difference across the surfaces should be equal. So what is the equation for the pressure difference? Delta P is equal to, tell me the equation.
40 over R.
Good, 40 over R. You didn't miss that. Some people say 2T over R. So remember, when there are two free surfaces, okay, you have to say 40 over R. So the 40 over R should be equal for all three systems. So here 40 over R, here 40 T1, okay, T2 over 2R, here 43 over 3R, simple. So when you cancel all the 4s and all the R's, you get the answer. What's that answer? $36. Okay. So I think we will not be able to complete all the questions today. Okay, now 37th. 37th is a very like students feel that question very difficult, but it's not. A cylindrical copper block of radius r and length 2r radiates as a black body at temperature T. If this copper block is cut and separated into n identical disks having same radius r, the rate of emission of radiant energy at the above temperature will increase by the factor of. So they ask me about the factor, okay, or the value. The factor means how many times. how many times greater. The new value is how many times greater than the initial value. So you know about the blackbody radiation. Can somebody tell me what's a blackbody? Can you tell me what a blackbody is? Blackbody is a body that radiates and also absorbs radiations of all wavelengths. Okay, so if you graphically put forward the distribution of different wavelengths from a black body for their, for their what do you call that? For their rate of, intensity, the intensity of the radiation. So it has a unit of, it's not actually intensity. It is called radiance, okay? Radiance. Yeah, radiance. It has a unit of watt meter minus 2, angstrom or nanometer minus 1. Okay, so it is the intensity per wavelength. So it should have the unit of angstrom. So it has a distribution like this. So it is emitting all the radiations ranging from 0 to infinity, very high wavelengths. Okay, so what do you call this? It's called lambda m. In words, how do you call that? The wavelength corresponding to the maximum intensity. Okay, this is a maximum wavelength. This is wavelength corresponding to the maximum intensity. So this thing is called maximum intensity per unit wavelength. Okay, E max. The area that this graph encloses is what? This is the power per unit area, that is the intensity of that particular wavelength. Okay, for example, delta lambda for that particular wavelength, belonging to that particular wavelength. So what happens to this graph when you increase the temperature? It displaces towards which side? Left side or right side?
Right.
No, left side, no? So this wavelength decreases, the area that the graph encloses increases. Okay? So this is how a blackbody radiation is explained. And so one person actually gave an equation for the intensity. Okay, for the intensity E. Usually I, but it's E here. So it is directly, he said that it is directly proportional to the 4 to the power of the thermodynamic temperature, Kelvin temperature, T to the power of 4. Okay, sorry. I think I became tired, I think. Sorry. I will try to be active. Okay. So now, who put forward this equation? It was Stephen. So Stephen says that the intensity of the radiation radiated by a black body is directly proportional to the T to the power of 4. So E, when we convert this relationship into an equation, we put a constant. What do you call that? Stephen's constant. Okay. So this thing is actually the intensity. Intensity is the energy emitted, or the energy emitted per a unit time from a unit area. So this is power divided by area. So when you make the power a subject, this is the expression for power. Okay, now they are actually considering a cylinder, copper cylinder, a cylindrical copper block as a black body, and now they are making it into separated into identical disk. So now the factor that changes here is the surface area, and they now want us to compare the radiant energy per unit time. Okay, so rate of emission of radiant energy. So we know as these two are constants, so P is directly proportional to E. So when it was a cylinder, you know, cylinder has two circular faces and one round face. No? So these two circular faces have a surface area of what? Pi r squared each. And what about the surface area of the rounded face? 2 pi r into L, no? So 2r. So that is here the length is L is 2r. So we have to put 2r. So this is this is 4 pi r squared, and these two give totally 2 pi r squared. So total area is initially P1 is directly proportional to 4 pi r squared plus pi r squared plus pi r squared, 6 pi r squared. So now there are n number of disks. Okay, so now the area is different. So let's find the area. P2 is directly proportional to the new area. So still you have the rounded face, so that the area of that face remains constant, because when you attach them, whether you attach them or separate them, you get the same surface area of the rounded face. No? So that remains constant, that is still 4 pi r squared. You can imagine that if you fix them again and make a cylinder, it's going to be the same. But what is the change that occurs here? What is the extra thing that happens due to the separation? It is the increase in the circular faces. So now each disk is going to have two circular surfaces. So if there are n number of disks, now there is n pi r squared circular faces. So now you have to put plus n pi r squared. Okay, now if we divide this equation, so sorry, each has two surfaces, no? So n into pi r squared into 2. Multiplied by 2. So the new one, P2, over the previous one, the ratio will be equal to what? Let's try to solve this. So 4 pi r squared plus 2 pi r squared into n over 6 pi r squared. So if you cancel all the pi r squared, and if you cancel everything by 2, so it is n plus 2 divided by 3. Very easy. Okay, so the correct answer is what? The second answer. Am I correct? Okay. Just have a cup of water and come. There are only 2 questions we have to discuss, and then we shall discuss the others later. So now 38th question, it's a very traditional one. It also doesn't deserve to be the 38th question. Okay. So now 38. Consider 2 motor vehicles, A and B. The motor vehicle A only front wheels are coupled to the engine and rotated. The vehicle B, only the rear wheels are coupled to the engine and rotated. Which of the following diagrams correctly shows the directions of the frictional forces acting on the front and the rear wheels of motor vehicles A and B by the ground when they are traveling in the forward direction? Okay, they're traveling in the forward direction. So you know which is the forward side, which is the front side of the car. Yeah, usually the front side is a little bit. So usually the front side is, where's the marker? Front side is a little bit protruding. So using that you can identify, and there is steering also shown. Okay. So don't argue that I took the front side the other way. Okay. So think naturally, like a person living in Earth. Okay. So now what is the significance of wheels being connected to the engines? So this is the front side. So this is the forward direction. So if the front wheels are coupled to the, when the front wheels are coupled to the engine, so what does the engine do? Engine tries to rotate the wheels. Okay. So it's like we are walking. And what do? We give a particular movement of brain due to the coordination. It gives a particular kind of a movement to your lower limbs. So when you try to run, you have a different type of movement. So like that, wheels are also like that. The wheels also have some kind of a movement to get an acceleration, to get a great acceleration, a low acceleration. According to that, it has movement. So both are same. So how do human beings get a force to accelerate? So usually when you want to accelerate, you actually press on the earth. No, you give some force using your foot. Okay, mainly using a thumb. Sorry, not thumb, the great toe. So you actually push. Okay, you push on the ground. So now you get the reaction like this. So it has a horizontal component and a vertical component. This is a normal reaction, and this is what? Friction. So due to the friction, you get a resultant force for acceleration. So like this, in a car, the wheels that are connected to the engines act. Okay, so act like this. The wheels that are connected to the engine is similar to this scenario. Okay, so now when they are rotated, okay, they are also pushing against the earth so that they will get the resultant force in the forward direction if they are connected to engines. Okay, so now you may think that usually the friction is what? Something that opposes the movement. So it doesn't happen here. No? Why is that? It is supporting the movement. Why? Is it supporting the movement? Actually, not exactly. Okay, it doesn't support the movement. You are actually trying to slide. Okay, you are trying to slide, but it opposes your sliding. So it has to give a forward force. So we make use of that force. So this is also, if you put a lubricant here, so it will like rotate in the same place. Why? Because it slides. But it tends to slide and gets what? A forward force to rotate. So rotation is actually an alternate for not being slided. Okay, so it's an alternate. So actually our friction does that alternate. It actually supports that alternative motion. Instead of sliding, you just go forward like that. It pushes. So it is not against the concept that friction always opposes the motion. It opposes sliding. Okay, but it supports the rolling. So when this is connected to the engine, the rest of the car is pulled by the engine and these two wheels. So the rest of the car is actually moved like this. So to oppose that, the other wheels will have friction like this. Okay? They don't have a driving force like engine gives to these wheels. They have a pulling force due to the front wheels like this. So to oppose that, there is a frictional force like this. So again, this frictional force rotates the car wheels. Okay, this force actually rotates. So both forces are actually helping the car to accelerate. Okay, so the correct answer is when you what is connected? Front wheels. So front wheels in the direction, the friction is in the direction of the motion. Okay, so fourth answer is correct. Okay, the last question that we are going to do today, 39th question. Consider the following physical phenomena. A, flowing water through a tube having two different areas of cross-section. The speed of water at Y is greater than speed of water at X. The second phenomena. B, gradual narrowing of cross-section of a water column falling down freely from a tap. So here, the gradual narrowing of the cross-section, okay? The third one, C, deflection of a cricket ball which is moving while spinning. So that is C. The D one, existence of a height difference in the liquid columns in vertical tubes. So now the question is, which of the above phenomena can be explained using Bernoulli's theorem? So what does the Bernoulli theorem say to you? So Bernoulli theorem says that P plus half rho V squared plus H rho G is a constant. So this is actually derived from the law of conservation of energy. So how do we derive this? The work done by the pressure difference is equal to the increase in the potential and the kinetic energies of a unit volume of liquid. So it's a basic concept. You can derive the equation by yourself. It's very easy. Okay, but it's not in the syllabus. So when you derive it, you finally get this relationship. Okay, you get this expression. It says that the sum of these three components is same in a streamline. Okay, along a streamline at any point. Okay, so now the P is actually called static pressure. Okay. P is static pressure. Half of V squared is kinetic energy per unit volume. This is potential energy per unit volume. So you know this is actually determined by the velocity or the cross-sectional area. Okay, the velocity is affected by the area of cross-section. This is determined by the height. This is determined by these two. Okay, that's how you explain this equation. So now let's see in the first diagram. One part of the tube is a little narrow. The rest of the tube has a larger caliber. Okay, so this one actually has a narrower caliber. So due to the reduction in the surface area, according to what equation? Continuity equation. A1 V1 is equal to A2 V2. Due to the reduction A, the V should increase. Okay, in a steady flow. So that the velocity here increases. So due to that, if you analyze that particular scenario using the Bernoulli's equation, H is constant. When you consider a streamline like this, there is no difference in H when you compare this part of the liquid and this part of the liquid. No difference in H. but the B is increased, so P should reduce. So if they talk about the velocity and also the pressure, that is actually explainable by the Bernoulli's theorem. But they are only mentioning about the change in the velocity. So that is explained using the continuity equation. There is no job for Bernoulli's equation here. The second scenario, again, gradual narrowing of the cross-section. The area of cross-section changes with the velocity. So due to the gravitational acceleration, and also due to this effect, due to the reduction in height, the velocity increases. In that scenario in B, the P remains constant, that is atmospheric pressure. So due to the increase in the velocity, there is reduction in the surface area. Surface area of cross section. So that is again continuity equation. Am I correct? If they tell about the increase in the velocity, that is explained by Bernoulli. But if they talk about the reduction in the cross section, that is explained by continuity equation. So you should carefully think here. So B is also wrong. Okay. C, deflection of cricket ball, which is moving while spinning. So this is an implication actually. It's an implication of Bernoulli's equation. Okay. So when you have a rotating ball, what happens is there is no change in the streamlines, but when it rotates like this, they say that this has a tangential velocity in this direction, this has a tangential velocity in this direction, air has a velocity in this direction, and the ball is moving like this. Okay, here the resultant velocity is high. Here the ball is opposed by the air. So here the resultant velocity of the air is low. So the pressure here is low and here the pressure is high. So with the higher pressure, it is deflected like this due to the resultant force. So that the C scenario is actually explainable using the Bernoulli's equation. With the increased velocity, decreased pressure. Explainable. The C, existence of height difference in the liquid columns in vertical tubes. Okay. So here there is a vertical tube. And here in the narrow part also there is a vertical tube. So here what determines the heights of liquids in the vertical tubes? Actually the pressure here. If the pressure is high, it shoots up to a higher height from this level. Again here, reduced pressure, lower height. So that is explained using our Bernoulli's equation. Now listen to me carefully. So here the higher surface area, low velocity. Here reduced surface area of cross section, not surface area. Area of cross section is higher, so velocity is lower. Area of cross section is lower, the velocity is higher. So the pressure is low, so the height is low. Here the pressure is high, the height is high. So that it's explainable using what? The Bernoulli's equation. When the velocity increases, the pressure decreases. Here the H rho G remains same. Okay. So C and D are explained. C and D are explained using the Bernoulli's theorem. So C and D only correct. Okay, are you all clear?
Yes, sir.
Okay. Shall we wind up the session? If you don't have any doubts, so I mean, ask any doubts if you have. Any doubts in any section, you can ask. Okay, thank you very much.